So the purpose of this video is to talk about divergent plate boundaries. By now you should be aware that there are three different types of plate boundaries. You have divergent, convergent, and transform plate boundaries. And so what we're going to be drawing today is an example of a divergent plate boundary out in the middle of the ocean. So let me get an appropriate color. And let's start with the far out view. So there's the seafloor. There's sea level. And let's draw in the entire thickness of the oceanic crust. Oceanic crust is here, gets thinner as we get towards that ridge. And then we have another surface right here. I should go ahead and note the difference between the solid lines and the dashed lines. The solid lines, I'm using solid because those define actual surfaces that you could, in theory, put your finger on. They are distinct, clear boundaries. Whereas I'm using a dashed line to represent boundaries that aren't so sharp. They're more gradational boundaries. There's not a sharp change from within a couple meters, but it's a gradual change. So we have, this is the oceanic, O-C-E-A-N, crust. That upper portion as oceanic crust. And all of this, because the crust is included, is the oceanic lithosphere. Oceanic lithosphere. And then under here, we have the asthenosphere. Okay. First and foremost, what's happening? Well, by now, you should have watched a video on plate tectonic processes, and you should be able to tell me that the plates are moving away from each other. So I've got little green arrows indicating the direction of motion. So these two plates are moving away from each other about a center called a mid-ocean ridge or a spreading center. At that spreading center, asthenosphere, which is solid, kind of migrates up because of less pressure. It's solid at this point, but it's moving up. And as part of that movement upward, it actually starts to melt. This is a process called decompression melting. When you have something of a particular temperature at a certain pressure, a certain depth, and you keep the temperature constant, but you remove pressure, the result will be a change from a solid state to a liquid state, or if it was already liquid, a liquid to a gas state. So we have the development of magma from a process called decompression melting. Magma from decompression melting. The asthenosphere is decompressing, and that is the process causing the melting. And the chemical composition of the magma is basaltic. We get basaltic magma from decompression melting. That magma rises and either solidifies just before it erupts, or it erupts and solidifies on the ocean floor. And the oceanic crust, we have new oceanic crust from crystallized magma. So we're constantly producing new oceanic crust from crystallized magma as long as the plates are moving apart. There's a couple implications for this. The first is that as we go further away from the spreading center on either side, we get into progressively older oceanic crust. Oceanic crust at this location is older than oceanic crust at that location, which oceanic crust here is older than oceanic crust at that location, etc. And the same thing can apply right here. This oceanic crust is older than that oceanic crust, and so forth, because all new oceanic crust is at the center. There's another implication. I really need more colors. Another thing that happens is we have planktonic life living in the upper oceans. I'm drawing little dots up here. And that planktonic life lives and dies, and as they die, little shells that they create sink towards the bottom of the ocean, and they accumulate along with other sediments. And it turns out that older oceanic crust has thicker seafloor sediments. That there's a cover on top of the basaltic oceanic crust. There's a cover of a thin layer of seafloor sediments that lay on top of it, and those sediments get thicker the further away that you are from the mid-ocean ridge, or the older the oceanic crust gets. And that's true on both sides. I could draw the same thing over here, but I'm going to save this side for another view. The other view is that older oceanic crust is deeper below sea level. So new oceanic crust is kind of at a high point below sea level, and further away you get from that, the seafloor gets deeper and deeper. And this is because the oceanic lithosphere, not just the crust, but the entire lithosphere, becomes more dense, and it sinks down. It sinks down further. And so therefore, older oceanic crust gets deeper below sea level. I'm going to now zoom in to this area, and we're going to talk about some things that occur on a much smaller scale, although they're quite large. So I'm going to draw that mid-ocean ridge. So there's the mid-ocean ridge. This is the sea floor. Sea level is up there. We're really at a zoomed in view. Let's draw in our body of magma and the base of the oceanic crust. And what I want to talk about is the eruption of this magma. This magma will follow conduits and erupt along breaks in the rock. These breaks in the rock are faults. Faults are break in the rock in which there's sliding, relative sliding of the rock. And those faults are important because there are earthquakes that occur along those faults. So I have little X's for where earthquakes occur. Earthquakes occur at mid-ocean ridges. And we also have the eruption of basaltic lavas, but some of those basaltic lavas or some lavas crystallize at depth. I believe this is everything that I wanted to talk about for divergent plate boundary processes. So I hope that you got all that. And if you have questions, let me know.